When we originally defined an ellipse, we defined it as a certain cross-section of a cone. And then after, we had a definition involving two foci and a chosen distance, which we called 2a. It's not at all clear what these two definitions have to do with each other, or even that they give you exactly the same shape, the ellipse. So we should somehow convince ourselves that those two processes really produce the same shape. Just to remind ourselves what those two definitions were, for the cross-section of a cone, you start with a cone, something like this, and then slice this cone with a plane. And if the plane is at an angle but not too sharp an angle, then the cross-section looks something like this. And if you reorient this plane so that you're looking at it straight on, the shape that you get is like this, our familiar ellipse. So that's the first definition that produced the ellipse. The next definition that produced the ellipse was you choose 2 points, which we called foci. So there's F1 and F2. And then you also choose a distance that we called 2a. And then the ellipse is made up of all of the points P, so that the distance from one focus to that point plus the distance from the other focus to that point together add up to 2a. So this point P would be one of the points on the ellipse, and there's another one over here and another one down here, and there's a whole trail of them that go around. And if you put all of them together, you get an ellipse. I have a very poorly drawn ellipse here. It's not really clear what these two definitions have to do with each other. Before we dive into seeing why these two constructions give you the same shape, there's actually one fact about geometry that I'll need to set up. So here's a sphere. This. I'm sort of drawing the equation or the equator of the sphere just to make it look more three-dimensional. And if you have any point outside of a sphere, if you imagine all of the tangent lines that go from the point outside of the sphere and just skim the edge of the sphere like this, all of these tangent lines intersect the sphere at a single place, and there is a line segment from the point off of the sphere to the point on the sphere. I've drawn just 2 of them. You can see really there's a whole circle's worth of them that go something like this. So another typical tangent line would be from this point over to the point off of the sphere. And it's a geometric fact that all of these line segments that go from a tangent point to this far point that's off of the sphere, all of these have the same length. That's sort of true. It's sort of obvious intuitively. You sort of imagine that all of these tangent line segments sort of form a party hat that's sitting on top of a sphere. And the party hat has the same length from its rim to the tip, no matter which direction you go down the party hat. So it's sort of geometrically obvious that all of these line segments are the same length when all of these line segments are tangent to the sphere. Okay, so with that geometric fact in our back pocket, let's look at our 2 geometric constructions of the ellipse. So our first one was starting with a cone. You slice the cone with a plane, and the intersection should be an ellipse. And you can kind of see the ellipse showing up right here. Let's emphasize that so we can see it a little better. There we go. There's our ellipse. Okay. And now we're looking for the foci, because if we can find points that we think are the foci of this ellipse, then maybe we can convince ourselves that the distance from the foci to the edge of the ellipse always adds up to the same thing. But where are the foci on this ellipse? It's a little bit hard to tell. You might guess that, well, maybe it's the intersection of the ellipse with this z-axis that's pointing straight up, but actually that turns out not to be the case. So it's kind of hard to see where the foci might be. Well, one day in the 18th century it was, thousands of years after the ancient Greeks invented all these shapes, in the 18th century somebody thought, well, what if we nestle a sphere into this cone so that it's just touching the ellipse? You can do that in two ways. There's this sphere that's on top, and it touches the ellipse right about here where I'm pointing with my mouse. And then there's this sphere that fits down below the slicing plane so that it's touching the cone, and it touches the ellipse at this upper left point that I'm pointing at with my mouse. So it's sort of geometrically intuitive that these two spheres are the only two spheres that do this. If you imagine just dropping a ball into a cone like this, it's going to settle down so that it is touching the cone around the edge of the sphere. And if you choose just the right size sphere, then it will also just barely touch the ellipse here. Okay, so we have these two special spheres for this cone and this plane. And they are tangent to the cone around their edge, and they touch the ellipse at a single point for each cone. In fact, why don't we emphasize those points by marking them. There are the 2 points where the spheres intersect the ellipse. You can see, looking at the edge of the ellipse like this, that these 2 points are on the plane of the ellipse and also on the sphere. And if we sort of look at this from above, looking at that ellipse, it looks like those points, those might be the foci. Well, to see if these are the foci, what we should do is choose a point on the ellipse, like there, and measure the distance from one of those points to the outside point, that's the green line segment, the distance from the other supposed foci to the point on the ellipse, and then check, as this point moves around the ellipse, is the sum of these two distances always the same? Well, if I drag this point around the ellipse, you can see the green line segment gets longer and the yellow one shorter, and if you go further, the yellow one gets longer and the green one gets shorter. So it's very hard to tell if the sum of these two distances, the green and the yellow, is actually always the same, no matter what point we're choosing on the ellipse. So we have some work to do to convince ourselves that this sum of distances is always the same. Okay. Well, if you look carefully at this green line segment, it is tangent to the bottom sphere. It has to be tangent to the bottom sphere because, first of all, it intersects the bottom sphere because this green line segment goes through this left-hand supposed focus, and this left-hand point here is where the bottom sphere touches that slicing plane. So the green segment intersects the sphere at this point, but even more than that, it has to be tangent to the sphere. So this green line segment is tangent to the bottom sphere because the bottom sphere is tangent to the slicing plane, and the green line segment is in the slicing plane. So the green line segment is tangent to the bottom sphere. For exactly the same reason, the yellow line segment is tangent to the top sphere. Now remember what we said about line segments that are tangent to spheres. If we have two line segments that from a single point that are tangent to the same sphere, they're the same length. Well, the yellow and the green line segments, they're both coming from this point on the ellipse, but they aren't tangent to the same sphere, so that we can't argue that those are the same length. Indeed, they aren't the same length. But let's go looking for another line segment from our point on the ellipse to the bottom sphere that is tangent. Well, there's one sort of special direction that we could go from this point on the ellipse and end up tangent to the bottom sphere. And it's this direction. If we follow the ray from the apex of the cone up to the point on our ellipse, there's one spot where this dotted black line is tangent to the bottom sphere, and that's down here. In fact, why don't we emphasize that point? It's this point right here. If we do the same thing for the top sphere, we get this top point up there. Notice that these two new points, these are on these circles where the spheres are resting against the cone. Okay? And this gives us two new line segments, the solid green line segment and the solid yellow line segment. Now looking at the two green line segments, the dotted one and the solid one, both of these line segments are coming from the point on our ellipse, and both of them are tangent to the bottom sphere. But by our sort of party hat argument, that means these green line segments have to be the same length. By the exact same argument, the two yellow line segments are the same length. Both yellow line segments are coming from the point on the ellipse, and they're both tangent to the top sphere. So by the party hat argument, the two yellow line segments are the same length. So we were trying to figure out why the green plus the yellow has to always be the same. But instead of thinking about the dotted green and yellow, look at the solid green and yellow instead, because those are the same lengths. Now as this point on the ellipse travels around the ellipse, look at the yellow line segment and the green line segment. They change length, but when you put the green together with the yellow, you're always going from this circle where the bottom sphere is tangent to the cone to the circle where the top sphere is tangent to the cone. And as you go around, the distance between these tangent circles on the spheres is always the same. If we erased the slicing plane but kept the spheres, we could still measure this diagonal distance. So the distance between these circles is the same along the cone, and that means the sum of distances to the foci is also the same. This argument to show that the two definitions of the ellipse really do produce the same ellipse took a couple thousand years for humanity to figure out. The ancient Greeks knew that these two definitions of the ellipse really did give the same shape, the ellipse, but their argument was sort of much more involved. So it wasn't until the 18th century that this new argument showed up. And it's one of the best ones I've seen, so I hope you enjoyed it.